Swayam Prabha. Digital India. Educated India.
In the last class we have discussed linearization of single variable systems. First we have linearized the nonlinear equation having single variable using Taylor series expansion, and in the next we represented that linearized model in terms of deviation variables. So today we will extend our discussion to linearization of multivariable systems. So today's topic is linearization of multivariable system. Fine. The approach is quite similar what we did in the last class. So today we will consider a multivariable system represented by these two equations, dx1 dt equal to function of x1 and x2, and another equation is dx2 dt, second function is f2, and that is also the function of two state variables, one is x1, another one is x2. And we will continue the equation numbers. I mean, yesterday we have considered up to equation number 15. So today we will start from equation number 16, and this is equation number 17. Fine. So this is the representation of a multivariable system. This is the representation of a multivariable system. So by multivariable system we mean a system having two state variables. By multivariable system we mean a system having two state variables. What are these variables? One is x1, another one is x2, and so these are two state variables, one is x1, another one is x2. Two functions are also involved, one is f1 and f2. Both these functions are nonlinear functions. These are nonlinear functions. Fine. So what we need to do? We need to linearize these two nonlinear equations by the use of Taylor series. Now according to Taylor series, what will be the linearized form of the first function, that is f1, x1 and x2? What will be the first term? First term will be f1, x1 naught, x2 naught. Fine. What will be the next term? Next term will be the differentiation of f1 with respect to x1, and we need to represent this at a particular operating point, that is suppose x 1 naught, x 2 naught. It will be multiplied with x 1 minus x 1 naught, fine. In the next step, we need to differentiate it with respect to second state variable, that is x 2. So, with respect to x 1 naught, x 2 naught multiplied with x 2 minus x 2 naught, fine. Next, we have to write the second derivative, dou to f 1 dou x 1 square at the operating point x 1 naught, x 2 naught, then whole square of this divided by factorial 2. Similarly, the second derivative with respect to dou x 2 x 1 naught, x 2 naught multiplied by x 2 minus x 2 naught whole square divided by factorial 2. What will be the next term? Dou to f 1 dou x 1 dou x 2 with respect to, I mean at the point x 1 naught, x 2 naught multiplied by x 1 minus x 1 naught, x 2 minus x 2 naught, fine. So, this is the linearized form according to the Taylor series expansion of the nonlinear function f 1. Similar expression we will get for the case of second function f 2. So, I am not writing that, fine. Similar expression we will get. Now, neglecting the terms of order 2 and higher, what we will get? Neglecting the terms of order 2 and higher, what we will get? If we write from dx1 dt dx1 dt, so it will be f1 x1 x2, fine. Since we are approximating this, so it will be f1 x1 naught x2 naught plus this x1 naught x2 naught multiplied by this plus dou f1 dou x2 at x1 naught x2 naught multiplied by x2 minus x2 naught, fine. This is the linearized form, and by neglecting the terms of order 2 and higher. So, we will give equation number 18 to for this, we will use equation 18 for this equation. Similarly, what will be the expression for the second equation, I mean second modeling equation? Please write the second equation also, dx2 dt, that will be f2 x1 x2 x1 naught x2 naught plus dou f2 dou x1 at x1 naught x2 naught multiplied by x1 minus x1 naught plus f2 dou x2 x1 naught x2 naught multiplied by x2 minus x2 naught. Fine. So, this is suppose equation number 19. This is equation number 19. What is the next step? We wish to represent this linearized model in terms of deviation variables. So, what will be the next step? We need to write the equations considering steady state. Fine. At steady state, we will assume that x1 naught equals to x1 s. Basically, we are replacing the suffix 0 by s. Fine. Similarly, we will write x2 naught equals to x2 s at steady state. At steady state, we will consider x1 s and x2 s. Fine. So, how we can represent the modeling equations at steady state? First equation will be dx1 s dt. x1 is s is a constant term, so we can write it as 0. This is equals to first function, and that is the function of x1 s and x2 s. Fine. So, this is suppose equation number 20. This is equation 20. Similarly, second equation we can write dx2 s dt equal to 0 equal to f2 x1 s x2 s. Suppose this is equation number 21. So, what we need to do in the next step to represent in terms of deviation variables, we have to subtract the steady state models from linearized models. Fine. So, next we will just subtract the equation 20 from 18. Similarly, we have to subtract equation 21 from 19. Fine. Basically, we are subtracting the steady state modeling equations from linearized modeling equations. So, what equation we will get for the first state equation? x1 minus x1 s dt equal to with respect to at x1 s x2 s x1 minus x1 s plus dou f1 dou x2 x1 s x2 s x2 minus x2 s. Fine. So, we will give some equation number, say equation 22. Okay. So, similarly, we will get for the second state variable, that will be d differentiation of x2 minus x2 s dt equal to dou x1 at x1 s x2 s multiplied by x1 minus x1 s, then partial differentiation with respect to second state variable x2 minus x2 s. Suppose this is equation number 23. Fine. Now, we assume the deviation variables, one is x1 prime, another deviation variable we assume x2 prime. What is x1 prime? x1 minus x1s. Similarly, x2 prime is x2 minus x2s. These are two deviation variables. Now, if we substitute these two deviation variable expressions in equation 22 and 23, what will be the expressions, I mean equations in terms of deviation variables? That we need to find in the next. We will just represent the equations 22 and 23 in terms of x1 prime and x2 prime. So, dx1 prime dt equal to, suppose we are using coefficients a11, a12, and for the next expression we will use a21 x1 prime plus a22 x2 prime. If we write in this way, so what will be the coefficient terms? A11 is x1s x2s, A12 is this one. Similarly, A21 will be this one, and fourth coefficient is A22, that will be x1s x2s. Fine. So, we got the equations. Now, we can represent those linearized equations in terms of deviation variables in matrix form. In matrix form, we can represent the final expressions like this. Fine. The dot symbol represents the time derivative. So, coefficient matrix A21 A22 multiplied by x1 prime x2 prime. Fine. Is this equation okay? So, this is the linearized form for a multivariable system. In this multivariable system, we have considered only two state variables. Fine. So, similarly, we can derive the expressions for more than two variables. Now, we will just take one example. We will take one example which has two state variables. So, we have considered previously one CSTR example, that we will continue to linearize using this Taylor series expansion. Fine. So, next we will consider one example. Which we have discussed earlier. This is a jacketed CSTR. The jacket fluid is entering here and it is coming out here. Feed is introduced with a flow rate of A5 concentration of CAI and temperature of TI. Suffix I indicates input, fine, and the product is coming out with a flow rate of F, concentration of component A, that is Ca, and temperature T. So, this composition is Ca, temperature is T, volume of the reacting mixture, volume of the mixture is suppose V. Previously we have considered one irreversible first order exothermic reaction. So, irreversible first order exothermic reaction, that is represented by this. A is the reactant and B is the desired product, fine. So, to remove the exothermic heat from the reactor, we need to introduce coolant stream in the jacket. So, this is basically a coolant which has the flow rate of suppose Fc and temperature is Tci. The coolant is coming out at the same flow rate Fc and temperature Tc naught, fine, and here we are assuming the temperature is Tc naught. So, based on the standard assumptions which we have considered earlier, we got three modeling equations. So, you recall these modeling equations. One is dV dt equals to Fi minus F, fine. F is basically the volumetric flow rate. This equation we got based on total mass balance. Similarly, we got another equation for component mass balance. Considering component mass balance, we got dCA dt equal to Fi divided by V CAI minus Ca minus K naught exponential of minus E divided by RT into Ca. This equation we got considering component mass balance, fine. Third equation we got considering energy balance. So, that equation is dt equal to Fi divided by V Ti minus T minus Q divided by V rho Cp plus minus of del H K naught Ca exponential of minus E divided by RT whole divided by rho Cp. This equation we got performing energy balance. You see, all these three equations are state equations because these equations have been derived by the application of the conservation principle on fundamental quantities, fine. Now, we have considered the formulation of linearization for two variable system. So, in this particular example, we will consider constant volume, so that we get two variable system, fine. So, in the we will discuss basically the linearization technique stepwise. So, in the first stage, in the first step, so this is suppose step 1, develop the dynamic model. In the first step, we need to develop the dynamic model. We will continue this example CSTR further assuming constant volume system. So, we are basically assuming here B is a constant quantity. If that is the case, then there will not be any existence of total mass balance. Fine. So, the modeling structure will reduce to a structure having two equations. So, we will write the final model structure dCA dt equal to 1 by tau CAI minus CA minus K naught exponential of minus E divided by RT multiplied by CA. Fine. Here tau is V divided by Fi. Fine. Tau is V divided by Fi. Similarly, we will write another equation, that is dt dt equal to 1 divided by tau Ti minus T minus Q divided by V rho Cp plus S K naught exponential of minus E RT Ca. So, what is S? S is minus of del H divided by rho Cp. This is S, and you see this S is a constant quantity. Fine. Similarly, tau is also constant. So, this is the final model structure which we need to develop in step 1. Next is step 2. Next one is step 2. In step 2, we need to identify the nonlinear terms present in the modeling equations. So, in step 2, we will identify the nonlinear terms which are present in the modeling equations. You see, in the first equation, I mean which we got based on component balance, the first right hand term, this is linear term. K naught is pre-exponential factor, so that is constant. So, only nonlinear term is here, this one, Ca multiplied by exponential of minus E divided by RT. That is the only nonlinear term present in the first equation. Similarly, in the second equation, first right hand term, that is linear term. Fine. Second right hand term, in this second right hand term, V rho Cp, they all are constant, only variable is Q. Fine. So, this is also linear term. In the third right hand term, S is constant, K naught constant. So, here also the nonlinear term is exponential of minus E divided by RT multiplied by Ca. So, in this model structure, there is only a single nonlinear term, that is exponential of minus E divided by RT multiplied by Ca. So, we will basically linearize this term using the Taylor series expansion. Fine. So, that is the third step. So, step 3, linearize the nonlinear term using Taylor series expansion. You linearize it, the nonlinear term. So, that is exponential of minus e divided by RT multiplied by CA. This is equals to exponential of minus e divided by RT naught multiplied by CA naught. Then we will derive this E divided by RT CA with respect to temperature. At T naught CA naught multiplied by T minus T naught. Similarly, we will differentiate with respect to CA at T naught CA naught, and we will multiply with CA minus CA naught. Here also we are neglecting the terms of order 2 and higher. So, what we will get finally? Finally, we will get exponential minus E divided by RT naught CA naught plus E divided by RT naught square exponential of E divided by RT naught into CA naught T minus T naught. Third term will be exponential E divided by RT naught minus E divided by RT naught into CA minus CA naught. Fine. So, in this third step we have just linearized the nonlinear term. In the next step, I mean in step 4, we will substitute this linearized expression in the nonlinear modeling equations. We will substitute the linearized term of e to the power minus e divided by RT CA in the nonlinear modeling equation. Substitute this. In place of this, you substitute this term, I mean this part. So, in step 4, we need to construct the linearized model. In step 4, we will construct the linearized model. So, for the case of concentration, we will get this equation dCA dt. First right hand term is 1 by tau CAI minus CA. Fine. Next term is K naught multiplied by the nonlinear term. So, K naught exponential of minus E divided by RT naught CA naught plus E divided by RT naught square E to the power, I mean exponential of minus E divided by RT naught C A naught T minus T naught, and the last term is exponential of minus E divided by R T naught multiplied by C A minus C A naught. Am I correct? Okay, fine. So, for the temperature, I mean dt equation will be, the first right hand term is 1 by tau in terms of temperature, 1 by tau multiplied by T I minus T, and Q divided by V rho Cp is there, that is also linear term. Then the third term was S K naught multiplied by that nonlinear term. So, we will just substitute here exponential minus E divided by R T naught C A naught, then E to the power E divided by R T naught square exponential minus E divided by R T naught multiplied by C A naught multiplied by T minus T naught. Last term is exponential minus E divided by R T naught C A minus C A naught. Fine. So, after substituting the linearized expression in the nonlinear model, we get these two equations. What is the next step? In the next step, we need to write the modeling equations at steady state, because ultimately we have to write the equations, linearized equations, in terms of deviation variables. So, step 5 is we have to write the modeling equations at steady state. So, represent the model, at steady state condition. Fine. So, if we represent at steady state, then we get these equations. It was dCA dt, so we are just adding the suffix 0 to represent the steady state. We are adding suffix 0 to represent the steady state. 1 by tau CAI naught minus CA naught minus K naught exponential minus E divided by RT CA naught. Fine. This is the steady state representation of the component mass balance equation. Similarly, if dt naught dt equal to 0 equal to 1 by tau T I naught minus T naught minus Q naught divided by V rho Cp plus S K naught exponential of minus E divided by R T naught C A naught. This is the steady state representation of the second modeling equation. Fine. So, sometimes we are using suffix s, sometimes we are using suffix 0 to represent the steady state. In the final step, that is step 6, we have to derive the linearized model in terms of deviation variables. So, we will write the final expression by subtracting steady state modeling equation from linearized modeling equations. So, step 6 is derive the linearized model in terms of deviation variables. Fine. If we subtract steady state equations from linearized modeling equations, we get these two expressions. I am writing those two equations. So, one is Ca minus Ca naught dt equal to 1 by tau Cai minus Cai naught. Next one is Ca minus Ca naught. Fine. Then k naught E divided by r t naught square e to the power minus exponential of minus e divided by r t naught multiplied by Ca naught multiplied by t minus t naught, and last term is k naught e to the power minus e divided by exponential of minus e divided by r t naught Ca minus Ca naught. Fine. If we subtract the steady state modeling equations from linearized equation, we get this component mass balance equation. So, we will represent this in terms of deviation variables. So, what will be that? d Ca prime dt equal to 1 by tau Cai prime minus Ca prime minus k naught E divided by r t naught square exponential of minus E divided by r t naught Ca naught t prime. Last term will be k naught E divided by r t naught square exponential minus E divided by r t naught multiplied by Ca prime. Fine. Here we are considering last term. This will not be there, no? Yeah, okay. So, this will be k naught exponential of minus E divided by r t naught Ca prime. Fine. So, here we are considering basically Cai prime, that is Cai minus Cai naught. This is one deviation variable we have considered in this equation. Another one is Ca prime, that is Ca minus Ca naught. Yeah, another deviation variable is here t prime. Another deviation variable is t prime, that is t minus t naught. So, this one and this one. So, 3 deviation variables we have basically considered. Fine. So, similarly, we need to write the equation in terms of temperature. That will be if T minus T naught dt equal to 1 by tau Ti minus Ti naught minus T minus T naught, then Q minus Q naught divided by V rho Cp plus is K naught multiplied by E divided by r t naught square exponential of minus e divided by r t naught C A naught t minus t naught plus exponential of minus e divided by r t naught into C A minus C A naught. Fine. After subtracting the steady state equation, we get this. So, if we again substitute the expressions of deviation variables, we will get d t prime dt equal to 1 by tau t I prime minus t prime minus q prime divided by v rho C p, then S k naught E divided by r t naught square exponential of minus E divided by r t naught C naught C A naught t prime plus exponential of minus E divided by r t naught C A prime. Fine. So, here one deviation variable is T I prime, that is T I minus T I naught. This already we have defined T prime. Another one is Q prime, that is Q minus Q naught. This is defined, this is defined. So, these are the two modeling equations for the example CSTS system in linearized form and in terms of deviation variables. Fine. So, next we will discuss the derivation of transfer functions, which is used in process control. So, our next topic is transfer functions. Usually the process is, the modeling equations are represented in time domain, but the transfer function is represented in S domain, Laplace domain. So, that job we need to do to represent the model in terms of deviation variables, in terms of in Laplace domain. So, first we will consider one process having inputs and outputs in time domain. Suppose this is the block of a process. Then this is the input to the process, which we will represent by f, and time we will use as independent variable. This is the output of the process, which we will represent by yt. Now, here by process we mean the model structure of the process. We will use the modeling equations of a process to derive the transfer functions. Fine. So, we will consider one example first, which is a single input single output system. First we will consider, we will derive the transfer function for a single input single output system, that is SISO. Fine. So, a single input single output process we can represent by this form, which is definitely linear or linearized version. A single input single output system we are representing by nth order linear or linearized equation, n minus 1 y dt n minus 1. We are trying to formulate in general, fine. That is why we have considered nth order equation, differential equation, a1 dy dt plus a naught y equal to b f t, fine. So, y is the output, f is the input, a and b they are the coefficients, and what else, t is the independent variable. So, as I mentioned that the transfer function should be represented in S domain. So, we have to take Laplace transform of this equation, fine. What is the Laplace transform? I mean, if we consider the Laplace transform of this dny dtn, this is equals to s to the power n y bar s minus s n minus 1 y naught minus s n minus 2 y prime naught, like this. Last term is y n minus 1 naught, fine. This is the Laplace transform of an nth order derivative. Now, if we consider in this equation, in this process model, y and f both are the deviation variables. These two are deviation variables. If that is the case, I mean, if y is the deviation variable, then definitely all these terms become 0, fine. So, we can write this as Sn y bar s. Similarly, we can consider another derivative. So, if we take the Laplace transform of this linear or linearized nth order differential equation, we get a n s to the power n y bar s plus a n minus 1 s to the power n minus 1 y bar s, like this, a 1 s y bar s plus a naught y bar s equal to b f bar s. Can we write this? If we take the Laplace transform of the linear or linearized nth order differential equation, we get this. Now, we can rearrange this equation like this, equal to b divided by a n s to the power n, a n minus 1 s to the power n minus 1, a 1 s plus a naught. This is the output in S domain, this is the input in S domain. This is the right hand side. This right hand side is basically the transfer function, which is represented by Gs. This is the transfer function. I mean, the transfer function is represented by Gs, and that is b divided by a1 s to the power n, a n minus 1 s to the power n minus 1, a 1 s plus a naught, fine. So, this transfer function basically represents the linear or linearized input output model in terms of deviation variables. You see, this is the input output model, fine. So, transfer function represents the linear or linearized input output model in S domain, Laplace domain. So, we have represented using the block the process in time domain. Now, we need to represent in terms of Laplace domain the whole process. How we can represent it? It is very simple. We will represent the process by GS here. Our input is, we will write in S domain. Our output is in S domain. Fine. You recall the representation in time domain. Now, in Laplace domain, I mean S domain, we will represent in this way. So, this is the block diagram. This is the block diagram of this process. Fine. So, this is the formulation of transfer function for a single input, single output system, SISO system. And in the next day, we will discuss multi input, multi output, single output transfer functions. Fine. Thank you.